Hello and welcome to this episode of 15 Minutes Hikkha. I am Amal Medhi from IISER Thiruvananthapuram. Today I will continue with part 3 and the last part of my talk on this topic, quantum physics up close. So before I begin, let me recap what I discussed in part 1. In part 1 of my video, I mentioned that quantum particles move in a way which is totally different from the motion of classical particles. In fact, quantum particles show both particle and wave-like character, and this behavior appears very strange to our human experience, and we don't have an intuitive understanding of the way in which quantum particles move. However, I mentioned that though we don't understand it intuitively, we can explain this motion by saying that there is a wave function associated with a particle, and the motion of a quantum particle is the consequence of the nature of the wave function. So in part 2 of my video, I said that when we deal with particles of microscopic dimensions, so there is a fundamental limitation in the way in which we make measurement, and it is in fact impossible to measure the position and momentum of a quantum particle simultaneously with absolute accuracy. So since we can't measure it, we cannot have a theory that talks about these two dynamical variables at the same instant of time. That means we can't use classical mechanics to describe microscopic particles. So also in the second part, I briefly introduce different formalisms of classical mechanics and use it to solve the equations of motion of a projectile, and so that using the equations of motion, by solving the equations of motion, we could predict the trajectory of a classical particle, and so I say that classical mechanics is predictive. Now in today's talk, what I am going to do, I am going to introduce the formalism of quantum mechanics. However, it will not be complete or comprehensive in any sense. I will give only the heuristic ideas, and will use this formalism to a few illustrative quantum problems. Okay, the aim is to give you a glimpse of what kind of physics the quantum mechanics give rise to. So before that, there is a statutory apology. Some discussions in today's talk may appear a little mathematically heavy for the general audience. However, for the physics part, it should be interesting to all nevertheless. Okay, so with this, let me go to the formalism of quantum mechanics. So the formalism can be stated by using a set of postulates. Okay, so here I will state the postulates, not all again, a few postulates to serve our purpose for today's talk, and to make the connections with classical mechanics clear, I will also compare the postulates side by side with what is the corresponding statement in classical mechanics. So here we go. So in classical mechanics, we say that the state or the dynamical state of a particle at a given time t is specified by two dynamical variables, that is x position and p momentum. In quantum mechanics, we say that the dynamical state or simply state of a particle at a given time t is specified by a wave function, which is denoted by the symbol psi usually. So this psi, it's a function of position x and time t, and it is a complex function in general. The second statement is, in classical mechanics, there is a special dynamical variable or dynamical function called Hamiltonian, which is defined like this. The Hamiltonian is sum of kinetic energy function plus this potential energy function. So in quantum mechanics also we have a Hamiltonian. However, now this Hamiltonian is not a ordinary function. Rather, it's said to be a quantum operator. Okay, so the kinetic energy function in classical mechanics becomes this differential operator in quantum mechanics, and this potential energy function is also taken to be a operator. So the Hamiltonian operator is sum of this kinetic energy operator plus potential energy operator. Now in classical mechanics, the equations of motion, or basically the state variables position and momentum, they satisfy the Hamilton's equations of motion, which are in a sense they are equivalent to Newton's equations of motion. But if we use the Hamiltonian formalism, so they will satisfy these differential equations and they can be easily solved to find out the x and p as a function of time t. In quantum mechanics, the state variable, that is that wave function, so it satisfies the so-called Schrodinger's wave equation. So this is also a differential equation. On the left hand side we have this time derivative of the wave function multiplied by this constant. On the right hand side is the Hamiltonian operator, okay, operating on the wave function. So this position and momentum and all other dynamical variables in classical mechanics, it can be determined by solving these equations of motions. Similarly, we can determine the wave function for a quantum particle by solving these Schrodinger equations of motion, and this psi mod square, it gives the probability that the particle will be found at a position x at time t. So this wave function has the probabilistic interpretation. So it keeps the probability, the mod psi square gives the probability that the particle will be found at a point x in time t. Okay. So similarly, the probable values of other quantities like momentum, energy can also be determined from the wave function. So since psi has a probabilistic interpretation, so we say that quantum mechanics is probabilistic. So now I will take this Schrodinger equation a little bit in more detail. So this is the Schrodinger wave equation and this is the Hamiltonian operator. So in situations where the potential energy of the particle is time independent, that means we can write V of xt equal to Vx, there is no time dependent. In that case, we can easily show that the wave function can be factored into two parts. One is the space part of the wave function, small psi x multiplied by a function, a factor which is function of time, exponential minus I e by h cross t. E represents the energy of the particle and h cross is Planck's constant. So that's the wave function. So we can also show that the space part, that is psi of x, which depend only on the position coordinate, it satisfies this differential equation, okay, which is also called time independent Schrodinger wave equation. Okay, and sorry, there's a mistake here. V doesn't depend on time. V is a function of x only. So we can take this time independent Schrodinger equation and solve this differential equation, and we can find the energy of the particle and also the wave function. So this is the basic formalism of quantum mechanics. So we can say that it is the central equation is the Schrodinger wave equation. So we need to describe any quantum system, we need to solve the corresponding Schrodinger wave equation. So here we'll use this formalism to the simplest mechanical system, that is the case of a free particle. A free particle is one which is not under any external force, and so the potential energy, potential experienced by the particle is 0. So in this case Vx is 0. So we use that time independent Schrodinger wave equation, put Vx equal to 0, and we get this differential equation, okay, which can readily be solved, and the solution will be of this form. So this k, the constant k is defined to be the square root of this constant 2m e by s cross square. So psi kx, because this solution will depend on the value of e or the value of k. So psi k of x is a constant a multiplied by exponential I kx. Now this function physically represents a plane wave. So the energy is given by s cross square k square by 2m, and in this case we can show that the momentum of the particle will be equal to s cross into k. So that's the momentum. So that means the energy of this particle is p square by 2m, which is exactly same equation for a free classical particle. For a classical particle, the kinetic energy is p square by 2m. So in this sense, in this case, for a quantum particle also, the energy expression is similar, same. However, if we look at the wave function now, the wave function, as I said, is a plane wave, and if we picture it, so it will look like this. This wave extends from minus infinity to plus infinity, and we see that, as I mentioned, so in this for this wave function, or in this state, the momentum of the particle is precisely well defined, and it is equal to h cross k. Okay, so there is no uncertainty in momentum here. Okay, so delta p is 0, and we in the second part of my talk, I said that we had a relation called equation. We have a condition, Heisenberg's uncertainty relation, which says the uncertainty in position and multiplied by uncertainty in momentum is operator of h cross. So in this case, since delta p is 0, the uncertainty in position, if you calculate, so it is turns out to be infinite. So which means that the position of the particle is completely undefined, which is also very clear if you look at the wave function, because the mod square of the wave function gives us the probability to find the particle at that point, and since the wave function is non-vanishing from it doesn't vanish anywhere, I mean it's non-zero from minus infinity to plus infinity, so there is a probability to find a particle anywhere, okay, from minus infinite to plus infinite. So its position is completely undefined, so which is drastically different from what our concept of a classical particle. Okay, and if you, so this is the complete wave function. You multiply the time factor, the other factor that depends on time, and so we get a complete wave function. And so this free particle wave function, it can be visualized also. So there is a YouTube video. I picked it up. So here, just look at this video.
In this scenario, we have a particle moving freely through space with a known momentum. However, the position of the particle is completely unknown because the amplitude of the wave function is the same everywhere. The square of the amplitude of the wave function at each location determines the probability of measuring the particle at that location. We can have some knowledge of the particle's location if the wave function consists of the...
Okay, so that's the visualization. So now let's mention about this aspect of quantum mechanics. So here the energy of the particle, as I said, is given by h cross square k square by 2m, and in this case the constant k, which is also called wave vector, so it can take any value between minus infinity to plus infinity. Okay, and therefore the energy can also have any continuous value between minus infinity to plus infinity. So then you might wonder that you have heard that in quantum mechanics the things are quantized, energy is quantized. So why in this case we are having I'm saying that the energy is continuous? So the answer is that the quantization of energy is not always necessary in quantum mechanics. So in quantum mechanics, things are quantized only if the particle is forced to be confined in a finite volume. Okay, so in this case, it's a free particle, it's unconfined, so the energy need not be quantized. Okay, so another question you might ask, or one may wonder, so then which particles are taken to be quantum, which particles are taken to be classical? Say we have a number of particles from big to small, so is there a hard boundary beyond which we can say that these are quantum and these are classical? The answer is no. Actually, all particles are, strictly speaking, all particles small to big, they obey quantum mechanics strictly, and classical mechanics is just an approximation. Okay. So, however, what happens is that in practice, the quantum effect of bigger particles is negligible, and so we can take them as a classical particle, or classical mechanics is good enough for to understand their behavior. So one aspect we can look into is the wavelength lambda of a particle. So of the wave function of a particle. So this wavelength lambda is given by h by the h is a constant, by p is the momentum. So in terms of energy, it is given by an equation like this, or this wavelength of matter wave we call it. So if we look at the wavelength for an electron, so the electron mass is of the order of 10 to the minus 31 kg. So if an electron is accelerated in an electric field of 1 volt per meter, say, and so for that energy, the electron, the wave function of the electron wave will be of the order of 10 to the minus 9 meter. Okay, so it's a very small distance, but still measurable. So it's it will have, it's still we can study its effects. Now if we take a small dust particle, let's say having a mass of 10 to the power minus 14 kg compared to electron, so this is a much heavier object, and if it is moving with a speed of 1 millimeter per second, then its wavelength will be equal to 10 to the power minus 16 meter, which is several orders of magnitude smaller than the electron wavelength. And so this kind of wavelength for the matter wave associated with the dust particle is very negligible for all practical purpose, and so quantum effects will be basically negligible. So we can take the particle to be classical particle. Okay, Then one more peculiar aspect is that the same quantum particle, they can exist in different avatars or different states. Okay, a classical particle can also exist in different state, but here it is slightly different. Okay, so for the free particle, I said that in the plane wave state, when the wave function of the particle is a plane wave, it has a well-defined momentum, but it has totally undefined position. Okay, however, this is not the only possible wave function for a free particle. So what we can do, we can construct another wave function by superposing infinite number of plane waves. So here it is mathematically written as an integration. So basically I am taking infinite number of plane waves, each with slightly different wavelength. Okay, and I am summing all of them together to get a new wave function. So mathematically this wave function is also a possible wave function or possible avatar or possible state for the particle. So I can choose this number coefficients zk in such a way that the final wave function phi x looks like this. So it's called a wave packet, okay, where the wave function is non-zero within a certain range delta x. Okay, beyond this range the wave function becomes zero, right? So in this case the particle has its position is undefined only to this distance delta x, and to construct this wave function, this wave packet, I have combined many plane waves with different momenta. So momenta got mixed up now, and so in this state the wave function doesn't have well-defined momentum. So it has a finite uncertainty in momentum, it has a finite uncertainty in position. Okay, so let's move to the next example. This is an example of a particle confined to a box. So we take a one-dimensional box, and let's assume these two are hard wall. The particle is moving in a one-dimensional axis or one-dimensional space between these two hard wall, and the potential function for the particle is given like this. So it is schematically shown here. So between these two walls, which are at the length of the box is L. So within this box the potential is 0. That means particle is free to move within this box, but it cannot go beyond this box. So at the boundary the potential is infinite, okay, both on both sides of the box. So now we so here as soon as the potential is infinite at this point and beyond, and this point and beyond, so the Schrodinger wave equation immediately implies that the wave function has to be 0 as soon as the potential is infinite. So in this case, though the particle is free inside this box, but the wave function must vanish at the boundaries. So again, to find the wave function, we write the Schrodinger wave equation, which is same as before inside this box. It's just that the wave function now has to satisfy two additional two boundary conditions. So for the free particle case, the solution of plane wave that we wrote is only a special solution for this differential equation. But now we have to take a more general solution, which is of this form: a sin kx plus b cos kx, and this function has to satisfy these boundary conditions. So once we impose these boundary conditions, so we'll get certain equations which will determine this constant a and b. and also it will, these boundary conditions or these equations will impose certain restrictions on the allowed values of the wave vector k, and it can easily be shown that in this case now the wave function will not be wave vector will not be continuous, so it will instead be discrete number, and it is given by n pi by l, where n is an integer which can take value 0, plus minus 1, plus minus 2, and so on. So now the wave vector is quantized, and as a consequence energy, which also depends on wave vector, will be quantized. So now it will get an index, so this energy values can be indexed by this number n, which is called the quantum number in this case. Okay, and the E of n will be given by this equation, so it will depend on this quantum number n. So that's the energy, and we can also find the wave function. It will turn out to be these functions. For n equal to odd integer, it will be cosine function. For even integer, it's a sine function, and we can graphically show these functions like this. So for n equal to 0 is will not be a physical state, so wave function is 0 there, so we have to neglect n equal to 0. For n equal to 1, so that's the lowest energy state. Lowest energy state is also called ground state, so that's the ground state energy, and the corresponding wave function will look like this. So which says at the boundary it vanishes as it should, and it is maximum at the center. So that means the probability to find a particle will be maximum at the center if the particle is in state n equal to 1. So this is the for n equal to 2, also these are called excited state. So this is the first excited state. In n equal to 2, the wave function has this form now, and you can see that the wave function is 0 at the center at the center. Okay, so also we call that it has a node at the center. So that means now the probability to find a particle at the center of the box is 0 if the particle exists, okay, in n equal to 2 state, right, which is very strange. You will not find a particle at the center of the box. So this is the n equal to 3 state, or the second excited state, and that's the wave function. So that's how it goes like, and it has infinite number of possible states. And like I mentioned before, it can also exist in a state which is a linear combination of all the states. So these are different avatars for the particle. Okay, so this example, what it shows that unlike classical particles, in this case the energy of the particle is not continuous. It can have only discrete values. Okay, and also you can see that the particle can be found at different point with different probability depending on which state it exists. Okay, the next example is will show whether we can trust in physics. So what I mean, so I'll show in a moment. So we'll now take the example of a simple harmonic oscillator, which is a very simple yet very interesting mechanical system. So the example is a simple pendulum. If you take the simple pendulum and pull it to one side and let it move, it will oscillate, and for small amplitude the motion of this ball or bob is called simple harmonic motion. So for such a particle, the potential energy is a function like this. So k is a constant which is not the same k as I mentioned before. This is called spring constant. So x is the displacement from the central position. The potential increases with as a square of displacement from the central position, and so it's a parabolic function like this. So if we take this particle to be a classical particle, so we can easily set up the equation of motion and find its solution, and we will easily find that the displacement of the particle, so if the particle is released from a, so this is central position, and if we release it from a distance a from the center, then it will this position will vary with time according to this function. It's a cosine function of time t. So in this case, so this a is also called the amplitude or maximum displacement, or it is also called turning point, because if we pull the particle to this point and release at this point, so what will happen? It will particle first move towards the center. So at this point it has maximum potential energy and zero kinetic energy. As it moves towards the center, its speed increases, so its kinetic energy increases and potential energy decreases. So this potential energy get converted into kinetic energy, and so here kinetic energy is maximum, potential energy is zero. After this, so as it it will overshoot the central position, it will go to the other side and its speed will come down. So this kinetic energy is getting converted into potential energy, and so it will come to this point minus a, where it will lose all its kinetic energy and everything will be converted back into potential energy. And if we assume that there is no other friction, no other external force on the particle will keep moving between these 2 points, minus a and plus a, and the principle of conservation of energy will tells us that the particle can never move beyond these turning points, so it will be confined in this region only. Okay, so we can trust that principle, and so we can do this experiment that I am showing you here. Again, one very interesting video taken from YouTube. Okay, that's what's this.
I am such a strong believer of the conservation of mechanical energy that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here. I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at zero speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it zero speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0. Physics works, and I'm still alive. See you Wednesday.
Okay, so we can trust the physics, right? So now let us see whether we can trust quantum particle in the same sense. Okay, for that thing, we'll now take that simple harmonic oscillator, not to be a big classical particle, but a very small microscopic quantum particle. Okay, So now if we take this to be a quantum particle, we have to again write the Schrodinger equations of motion, and now the potential is half kx square. So we need to solve this equation, so which it can be solved, and if we solve this, so we'll find that now the energy of the particle will again be quantized. Okay, it is given by relation like this: En equal to n plus half multiplied by a quantity called h cross omega. So this is the quantum of energy, and n can have only positive integer value in this case, can value take 0, 1, 2, 3 and so on. Okay, and the assuming this constant to be all 1, the wave function, corresponding wave function for the particle is given by a function like this: constant a multiplied by exponential minus half x square multiplied by a function called Hermite polynomial, which depends on the quantum number n. So this is the energy, these are energy eigenvalues, and these are the energy eigenfunctions or the wave functions for the particle. So again, the lowest energy state, that is for n equal to 0, that's called the ground state. So in the ground state, the particle will have energy half h cross omega. Okay, and the first excited state, it will have energy 3 by 2 h cross omega and so on. Now if we look at the wave function, if we plot it, so we will see a picture like this. So at the center, so this is the ground state wave function. So at the center, the wave function is maximum, and it decays exponentially away from the center, and it becomes 0 at a certain distance from the center. Okay. Now what these two dotted line indicates is, if the particle were a classical particle instead, and if it would be oscillating with a total energy of half h cross omega, which is same for this quantum particle, then that classical particle would never cross. So then these 2 points would indicate its classical turning point, its turning point. So this particle would have never crossed these 2 turning points, and it would be always confined in this region. So you could do that same experiment that I showed in the video, and then you could trust that it will not cross this point, and you will not get hit by the particle. But here you see that the wave function in this case is non-zero even beyond this classical turning point. So which means that there is a finite probability that the particle will be found beyond this classical turning point, right? So then what would happen if you trust the classical mechanics blindly, and you position yourself at this location here, and assuming that it will not cross this classical turning point, you can imagine naively what would happen. Okay, in any case, you can't do this experiment with a quantum particle. It's just a thought only. Okay, so this is very, very peculiar with quantum particle. So it can escape barrier. What is a classical barrier, which a classical particle can never escape, but quantum particle can do it. Okay, so this same kind of thing, if you look at the first excited state wave function, again it has a finite amplitude beyond the classical turning point. Okay, so this is another wave function, that's another wave function, that's another wave function, and so on, right? So it's very interesting. Okay, and yeah, so that is the message here. Okay, now I come to the final example here. So I talked about the projectile motion with a classical particle. So for that case, we said that there was a ball which is released from a height of say 500 meter with a certain initial velocity. So in that case, we ask that question: how did that ball would move, and at what point and at what time it will hit the ground, and what would be its trajectory? So that is the question we ask, and that we could easily find using say Newton's equations of motion. Now, can we ask the same question, or what would happen if this ball instead were a quantum particle? And you ask that question, I take the ball, I take the quantum particle at certain height and release it with a certain speed. How this quantum particle would move? Would it move? Would it follow the same trajectory as the classical particle, or something else would happen? Okay. The answer is the first answer is, in fact, that question itself is wrong. Okay, so we can't ask that question. So the first mistake is, we can't say that the quantum particle is at height 500 meter and it has a velocity of 1 meter per second. That would amount to specifying its position and momentum simultaneously, which is not possible for a quantum particle. So we don't have that information, so we can't state that. So okay, so at best we can say that let's say there's a particle, it has the initial wave function or initial state is like this, or it is okay, then we can ask this question. So given this initial state, what is the probability? We can ask about the probability. What is the probability that the particle will let's say hit this point on the ground at time t? That's the question we can ask. Okay. So the answer to that question, as given by quantum mechanics, goes like this. Okay. The answer is that, first answer is that when the particle move from here to here, it can move via any path, not only one path. Okay, that means it can move via path number this, which corresponds to the classical trajectory. It can also move by another path like this, path number 1. It can move via path number 2 like this, 3, 4, and so on. So it can move from point A to point B via infinite number of paths. So, and the quantum mechanics tells us what is the probability amplitude that this particle takes a particular path. Okay, so the probability amplitude attached to a particular path is a complex number, which is given like this. So it's exponential I of s by h cross. Now h cross is Planck's constant. Now this s is the classical action. It's a action for the particle. So I mentioned about classical action in second part of the video. So that action appears here now. So this is the probability amplitude attached to a given path, and since the particle can come via infinite number of paths, so this net probability that the particle will arrive at this point will be sum of all these probabilities. So sum over all paths and the quantities, the probability attached to that path. Okay, that's the net probability amplitude. And so, I mean, that net amplitude, what is this measurable quantity? It will be z mod square. Okay, so this is what the description of the motion in quantum mechanics. Okay, so this is basically ends my talk, and I hope by now you have you at least get a flavor of what quantum mechanics looks like, and also for students who are students of physics. So if you want to learn more, there are some books that you can go through. So these books I also mentioned before. So there are many good books. So and these books you can also see. So this is very comprehensive and book, and Feynman lectures, of course, conceptual aspects are there, and this is also very good, and this is lots of examples, calculations are there. Okay, and this books this is a volume 2. In fact, there are 3 volume book. It's a very detailed discussions. Okay, and for general audience who are not necessarily students of quantum mechanics, they can for example also read this very interesting book on the subject of quantum mechanics. They can read this book. Okay, so and this is my contact address. In case some student want me to ask some question, they can email me at this address, and also this is my phone number. Okay, so with this I finish today's talk, and thank you for all your attention.